Use mathematical induction to prove that for every integer n greater than or equal to 2, if a set S has n elements, then the number of subsets of S with an even number of elements equals the number of subsets of S with an odd number of elements. So we need to use mathematical induction on the number of elements in the set S, which means we need to start with our base case, which will correspond to when n equals 2. So we have to think about sets of size 2. Now this is pretty simple because even though we don't know what those two elements are, we can give them names like S1, S2. These are the two elements of our set S. Now let's consider all of the subsets of the set. So we first count all of the subsets with 0 element, and there's only one subset with 0 element, which is the empty set. Then we can consider all of the sets of size 1, which there are 2 of those, and we can consider the set of size 2, which there's only 1 of those. Now in this case, the number of odd subsets is 2. In this case, we're counting the singleton sets. And then the number of even subsets is also 2. We have the empty set, which has 0 elements. That's an even number. And then we also have the whole set itself, which is a set of size 2. So that's the base case. Now let's get to the hard part of this problem. We start the inductive step the same way every single time. Let k be an arbitrary fixed integer with k greater than or equal to 2, and assume that p of k is true. Now our inductive hypothesis p of k is the statement that every set of size k has the same number of even subsets as the number of odd subsets. Now we have to show that p of k plus 1 is true, which means that we have to show that every set of size k plus 1 has the same number of even subsets as the number of odd subsets. Now consider a set A with k plus 1 elements. We can write out what these elements are, and even though we don't really know what these elements are, we can give these elements names like a sub 1, a sub 2, all the way up to a sub k, and then a sub k plus 1. There's k plus 1 elements here. So we can give those k plus 1 elements names, even though we don't know what they are. Now we want to show that the number of even subsets of A is the same number as the number of odd subsets of A. Now the way we're going to do this is we're going to build a new set B. B is going to be the set A1, A2, A3, almost the same set as set A, except without that last element a sub k plus 1. So we're taking this element and we're removing it. So that means that the size of B, the number of elements in the set B, is k. And we know information about every set of size k. In particular, with this set B, we can use the inductive hypothesis to say that the number of even subsets of B is the same as the number of odd subsets of B. Now the next thing I want to do is I want to illustrate what's really going on here with this set B. What I'm going to do is I'm going to create 2 groups of subsets. Now keep in mind, these are not groups of elements of B. These are groups of subsets of B. And in particular, by the inductive hypothesis, if these are all of the even subsets and these are all of the odd subsets, then the number of even subsets equals the number of odd subsets. So the size of both of these groups, the number of subsets in each category, is the same by the inductive hypothesis. The next part of this problem is we're going to reintroduce this element a sub k minus 1. Now this is the hard part. This is very difficult to wrap your mind around. Consider all of the subsets of A, not the set B, but consider all the subsets of A that include a sub k plus 1. Now keep in mind, since B is a subset of A, everything in B is also an element in A, then that means that all of these subsets of B are also subsets of A. The trick here is that for every subset of B, we can include the element a sub k plus 1 to create a new subset. What we can do is we can take all of our subsets of B, which again are subsets of A as well, and we can imagine these subsets with a sub k plus 1. Now keep in mind, these even subsets don't have a sub k plus 1 because these even subsets here come from the set B, and B doesn't have a sub k plus 1. So each time we take one of these subsets and we include a sub k plus 1, we're getting a new subset of A. And in particular, if all of these subsets were even inside, then by adding one more element, we create odd subsets. So all of these sets with a sub k plus 1 are actually odd in size. We could do the same thing with all of the odd subsets. We can imagine these subsets with a sub k plus 1. Now, these subsets are also not in the subsets of B because it includes a sub k plus 1. A sub k plus 1 is not an element of B. But these subsets from B were odd in size. So by adding a sub k plus 1, then these are now even in size. And what's important is we're just taking all of the subsets that are even and adding a sub k plus 1. And we're taking all of the subsets that are odd and we're adding a sub k plus 1. So the number of odd subsets here is the same as the number of even subsets without a sub k plus 1. And the number of even subsets with a sub k plus 1 is the same as the number of odd subsets without a sub k plus 1. So to summarize what's really going on here, by including a sub k plus 1, we're creating a bunch of new possible subsets. And all of these new subsets can be derived from the previous subsets, the subsets of B, and then we either include or we don't include the element a sub k plus 1. All of the subsets that don't include a sub k plus 1 are here. And all of the subsets that do include a sub k plus 1 are here. And every subset either includes a sub k plus 1 or it doesn't. So all of these subsets correspond to all of the subsets of A. This is an organization of all of the subsets of A. But if you notice in this organization, the number of even subsets is equal to the number of odd subsets. By including the subsets with a sub k plus 1, we're essentially doubling the number of subsets of B. But since we're adding the same number of odd subsets as the number of even subsets, then that means that the number of even subsets of A is still the same as the number of odd subsets of A. And this proves that P of k plus 1 is true, because this means that for any set A that contains k plus 1 elements, then the number of even subsets of A is the same as the number of odd subsets. And so that means P of k plus 1 is true. And therefore, by mathematical induction, P of n is true for all integers n greater than or equal to, I think it's 2. Let's scroll back up. Yeah, it's 2 here, 2 here. Thanks everyone, and I'll see you in the next video.